Welcome back. Today let us continue with the analysis of the spectra of some other nuclei. In the last class, we understood about the multiplicity pattern. We understood how to analyze the proton spectrum based on the multiplicity pattern because of coupling with the neighboring groups. It could be both homonuclear or heteronuclear. And we took several examples how we can analyze the spectrum by using simply we synthesize the spectrum also. At the same time, we took the realistic spectrum and tried to analyze based on the multiplicity pattern. So that's what we did. So we got some hang of how to analyze the spectrum. What is useful information we require for this is coupling and also chemical CUT. The knowledge is essential to make the analysis of the spectrum. So we came to the carbon 13. We discussed carbon 13. We also understood carbon 13 is 1.1% abundant. Very difficult to see all the carbons in carbon 13 states simultaneously in a given molecule. So we discussed and understood it is a superposition of the spectra of n different spectra, each corresponding to one carbon in a carbon 13 state. Whereas the proton is 100% abundant you get from a single molecule. And for carbon 13 we also said the discussion is generally only based on the broadband decoupling. Carbon 13 spectrum is recorded only with broadband decoupling most of the time, unless you are interested in carbon proton couplings. That means simultaneously all protons coupled to all the carbons will be removed, what is called broadband decoupling, in which case you will see individual for each carbon one peak. If there are n peaks in the carbon 13 spectrum, you have n chemically inequivalent carbons present. But mind you, we are not removing the coupling with other heteronuclei. Like in a molecule has fluorine is present, phosphorus is present, which are all 100% abundance. There can be coupling with carbon, that we are not removing. Only broadband proton decoupling with carbon can be removed. Of course, in the present day spectrometers it is possible to remove various nuclei simultaneously. We can break the coupling with different nuclei also, it is possible. But generally this is what is done in the chemistry, broadband decoupling. And then we wanted to analyze some of the carbon 13 spectra. Let us see, after understanding how carbon 13 broadband decoupling spectra is seen for some big molecule like we saw small molecule and also big molecule, we will see how we can analyze that. I will take a simple example of a molecule like this. It is called acetic acid, CF3COOH. Now it is a carbon 13 NMR spectrum. I have told you it is a broadband decoupled, meaning there is no coupling of carbon with proton. Of course, there is only one carbon here, COOH, but that also is not coupled to carbon. And there are two chemically inequivalent carbons here, COOH carbon and CF3 carbons. Now what is the type of spectrum we are going to get for this? Very simple spectra we have got, we have to interpret it. Look at this one, there is a TMS. This is what used as a reference, we will ignore it. Here TMS has CH3 protons, but remember broadband decoupled is a single peak, no curve splitting at all. You come to this peak, there are 3 peaks of equal intensity. What are they coming from? This is the solvent we use, what is called CdCl3. Carbon 13 is coupled to deuterium. Deuterium is spin 1. As a consequence, you get 3 lines of equal intensity. That is why this is a solvent peak. But now look at this one. This is CF3. Of course, in this case what is happening is we get large quartet. Why this quartet coming? There are another quartet here with a small separation. There are 2 quartets coming. What are they? Why are they coming? Remember, this carbon is directly attached to 3 protons here. So as a consequence, what is going to happen? It is exactly similar to what you see in proton NMR, like proton couplings. Okay. So now this carbon can couple to this fluorine. As a consequence, the 3 chemically equivalent fluorine split this carbon into quartet. And interestingly, CF coupling is very large. This is of the order of nearly 300 Hertz, 284 Hertz. One bond carbon coupling is so large, around 300 Hertz and with a negative sign. So this large quartet with a large separation must be this carbon attached directly to fluorine. Okay, that is fine. What about this carbon? Why it is a triplet, quartet? Remember, This carbon has a long 2-bond coupling with this fluorine. These 3 fluorines simultaneously coupled to this carbon also. As a consequence, this carbon is going to be a quartet because of these 3 fluorines. And this coupling is very small, 44 Hertz. That is why the quartet, in the quartet you see adjacent line separation is small here compared to this. So, these 2 quartets are because of 2 different carbons which are split into quartet because of 3 equivalent fluorines. Directly attached fluorine carbon has a larger separation, larger quartet, and this is a smaller quartet. Very easy to interpret. If there used to be a proton coupling, then you would have brought coupling with OH protons and all those things. Now, we will go to the another molecule like this. It is a very simple molecule. It is a trifluoroacetate in CD3OD. Now, it is very difficult, looks like that very complex, and remember again it is broadband decoupled. It is carbon coupled, not broadband decoupled. This is the interesting thing. That is why this example is chosen to tell you. Now, carbon is coupled to proton. Very interesting thing should happen. What is the structure of this molecule? It is like this. CF3 C double bond O OCH3. Very simple molecule. How many carbons are there? 1 carbon, 2 carbon and 3 carbon. There are 3 different carbons. But see 1, 2, 3, 4, 5, 6 different peaks are there. Where are they? Why are they coming? What are those peaks? You have to understand that. First remember, at the reference 0 we have a quartet. This is what is the reference we use? TMS. TMS has a Si with 4 CH3 groups, and this carbon is coupled to 3 equivalent protons and gives rise to a quartet. As a consequence, at 0 reference you have a quartet. This is TMS, easy to interpret. Okay. Then this is multiplicity pattern coming because of coupling with deuterium. This is a solvent peak. This is a solvent carbon of the solvent CD3COCD3 which is coupling to deuterium D3, and it need not be 100% D3, it could be CD2H, CDH2, varieties combinations will be there, different isotopomers. As a consequence you get a complex pattern here. This is from the solvent, that also we understood. Now, how do you understand 4 different patterns? 4 different patterns. Now, you see one of them is a large quartet, large separation. In the previous example we saw this must be CF3 where carbon is directly bonded to fluorine, equivalent 3 fluorine. So, it is a CF3 per carbon. Then this carbon, this is carbon directly attached to proton, this is also a quartet, fine, that is also understandable. What about this carbon? This carbon is coupled to this fluorine, 2-bond coupling is there, 40 Hertz, we saw in the previous example. So, this is a quartet. But remember, if I expand this, each line of the quartet is a further quartet. It is a quartet of a quartet. What does it mean? That means this carbon is also coupled to these 3 protons. So, this is quartet because of these 3 fluorines, and each line of the quartet is further split into quartet because of these 3 protons. So, this is also understood. This is this carbon. Now, what is this isolated peak which is coming here? Where is it coming from? Remember, this is a carbonyl peak of the solvent CD3 COCD3 is there. This is CD3 carbon, whereas this is CO carbon of the solvent. That is how we can interpret the spectrum very easily. So, now all carbons can easily be assigned, solvent, everything, and you can measure directly CF coupling and also CH coupling because it is not proton decoupled. Okay. So, now with this carbon, of course, lot more things we can discuss. There is no time to spend so much of things. What we will do is, we will take some simple examples of spectra of few other heteronuclei. That is very important to understand spectra of few other heteronuclei. That can give us an idea how to analyze the spectra. Generally, of course, organic chemists or others concentrate on proton and carbon. If you go to inorganic chemists, people have different other exotic nuclei. They will be interested in studying different type of nuclei. Let us take the example of other some heteronuclei to analyze. We will start with analysis of the spectrum of a molecule like this. The name is like this, and its structure is very simple. There are only 2 tins present here. I am looking at the tin 119 NMR. Remember, I am looking at tin 119 NMR of this molecule, and this is the complex spectra you have got. and these regions are expanded here. This is a vertical expansion is given. So lines are, to make it lines very clearly visible. Now we have to analyze this. Why the spectrum is so complex? There are only two tins here. There are only two tin nuclei here, but spectrum is very complex. But remember, none of them are impurities or anything. They are real peaks from the sample. Then how do you interpret it? So first thing, before that we understand what are the salient points of the tin isotopes. Tin has three isotopes: tin 119, tin 117, tin 115. Interestingly, all are NMR active, all are spin-off nuclei. Also, an interesting point is all of them have negative magnetic moment. What does it mean? I explained to you. Remember, if it is a negative magnetic moment, the sense of their position is opposite. If the protons are precessing like this in the magnetic field, the tins will precess in the opposite direction. That is all the difference. Okay. But if you consider tin 115, its abundance is 0.34. You can practically ignore, and sensitivity is also very, very small. So practically we can ignore it. We don't have to worry about it. But we consider other two tin which have equal or natural abundance. Remember, tin 119 is almost 8.6%. This is 7.7%. Average, if you say all, both of them are around 8% abundance. So both are equally abundant almost. And sensitivity, one is about 20, other is 25. Sensitivity of 117 is 20, 119 is 25. Good. That is why we got the tin 119 spectrum. Sensitivity is better and spin-off nuclei of that molecule. Now our challenge is to analyze the spectrum, to interpret. You have to say which peak is coming from which. Each peak is, we have to make the assessment very clearly. No peak should be left out. We will start analysis like this. See, now we know there are two tins present. Here the concept of isotopomers you have to think. For example, there is one possibility where there are two tins which are present, and one is 119, other is 115, whatever it is. There is no coupling with any other thing. There are two independent tins which are present. Okay. So they are the peaks, two signals for two tin 119 in different environments A and B, and pertain to each containing only one tin 119. And there is no coupling with any of these things. Okay. Couplings are ignored here. There is no other coupling. So that means two peaks here, strong peaks we can assign for two different tin molecules containing tin 119 in different environments. In one case this is 119, other case this is 119, this is from 115 or so, which is not visible, not coupled at all. Fine. Now consider a possibility. Varieties of possibilities you can think of. Consider one possibility where the molecule contains one 119 and other 117. There are two tin isotopes and both are NMR active and both are spin off, both are equal abundant, almost equal, and both are very good sensitivity is there. That means there exists a coupling between these two. These two are adjacent to each other. There may be a coupling between these two. When you have a coupling between these two, we call it as an AX spin system. I have not introduced the spin nomenclature, I will come to that later, but remember it is called AX spin system. AX spin system is two weakly coupled spin system, each of them will give rise to a doublet. Simple logic, we discussed this when you understood the multiplicity. When one proton is coupled to another proton, this will see this in alpha and beta positions and become a doublet, and this will see this in alpha and beta position become a doublet. So like that, when two spins are weakly coupled, we get 4 peaks. That is exactly what we should expect. And then another interesting thing is tin 119 and 117 are separated by large chemical shift. In the sense, in a 500 megahertz spectrometer, the resonating frequency differ by about 8 to 9 megahertz. So you don't see both of them together. You see only one nuclei at a time. You can see tin 119 NMR, only tin 119 NMR. 117 peaks you don't see. For that you have to go to tin 117 resonance by shifting the resonating frequency a bit. Okay. So now we are concentrating on tin 119, although the molecule is present as tin 117, one of the tin. So what are the possibilities? We can consider two such possibilities like this. One, this could be 119, other this could be 117, or this could be 117, this could be 119. There are two molecules present now, both are different, and there is a coupling between them. As I said, This will be a doublet, this will be a doublet, this will be a doublet, this will be a doublet. How many doublets you expect? 4 sets of doublets you get. Okay, 2 AX pin system. You should get 8 lines. But remember, this is N117, TIN117. That coupling is seen, but this doublet will be seen only in the TIN117 NMR. So you will get only one doublet for this and one doublet for this 119. That's all you are seeing. So now this we have already analyzed, and then each tin give rise to one doublet because of its coupling with 117, 2 isotopomers. This could be one of them 2 doublets on either side, and other one, these are the 2 doublets on either side. So 4 peaks you identified. The remaining 4 peaks, where are they? That is seen in the TIN 117 NMR. Remember that. So 2 peaks we have already assigned in the possibility 2. Now possibility 3. Why can't we think of both 119? This pertain to an AX pin system. Again 2 protons are coupled, 2 tins are coupled. There is a, each of them will be a doublet. So what will happen? Then you should get how many peaks? You should get 2 doublets. 2 doublets means for each tin side on either side you should get 2 lines. It is symmetrically placed with respect to both the tin peaks. So this we have analyzed, and this peak we analyzed, these 4 peaks. Now what is left? See, this is one doublet, this is another doublet, which are symmetrically placed on either side. This is another doublet which you are trying to see that. Okay. Why it is intensity set small? That is a different question. We will not worry about it. This is again a little bit of involvement and discussion. We will keep it pending for that. Don't worry. These peaks or assignments are correct. So we assigned 4 peaks. Now possibility 3 is over. What is the possibility 4? One can be tin 119, other can be carbon 13. This is possible. For example, this can be tin 119, this is carbon 13. Can there be a coupling? Why not? Carbon 13 1%, 1.1% abundant. It couples to tin and gives rise to multiplicity. It can become a doublet. It's possible. And another molecule, this is 119, this is carbon 13. That's also possible. So there are again 2 AX pin system. There are 2 such possibilities, and you should get 4 doublets, 8 peaks you get. But remember, after the 8 peaks, 4 peaks are seen in this case, in this 119 spectrum, and the remaining 4 peaks are seen in carbon 13 spectrum. That is the difference. Okay. So 2 doublets are seen here at the chemical sheet of A and B. And now we analyze this, we analyze this, we analyze this, and now these 4 lines are analyzed. Fantastic. All peaks have been analyzed. All the peaks. So none of them are repeated except these small cases which are not from this molecule. So 2 sets of doublet, one each is seen at the chemical sheet of A and B. Okay. Now what happened to another set of 2 doublets now? That is seen in the carbon 13 resonance. There is a possibility, another possibility. What is that another possibility? Both could be 117. It is possible. But remember, you don't see in 119 because it is a passive spin. If you want to see this, you have to go to TIN 117 NMR. Remember, you record a TIN 117 NMR, identical spectrum you are going to see for that also. And that is why we are not going to see this in 119 NMR. So this will be seen in TIN resonance of TIN 117. Now what is the possibility 6? Very confusing, right? Now this could be 117, this could be carbon 13, or this could be 117, this could be carbon 13. Again you get 2 AX pin system. 2 AX pin system means each will give rise to 4 peaks. There will be 8 peaks actually. 4 is seen in TIN 117 NMR and the remaining 4 seen in carbon 13 NMR. Both of them we don't see in this spectrum. This is the possibility. So very simple molecule. Look at the complications. Only there are 2 tin atoms are present in the molecule, but because of the isotopes abundance and different isotopomers are present in the molecule, so many possibilities one can think of, and each peak can be clearly assigned. This is the beauty of NMR, where small microscopic perturbation at the site of one of them because of isotopic substitution is clearly visible in the NMR spectrum. That is how, understanding the isotopomer spectrum, we were able to analyze this in NMR. Okay. Now we will go to another exotic nuclei, phosphorus NMR. This is something which most of the time biology people use. They study P13 NMR, 31P NMR. Interestingly, it is a spin-off nuclei, friendly nuclei for us. Also 100% abundance, very easy. Phosphorus, fluorine and proton, they are all friendly nucleus to study because 100% abundance and spin-off nuclei. Look at this molecule. This is a very simple molecule and PF3H. There are 1 proton and 3 fluorines. Now, these 3 fluorines are equivalent. Then what is the pattern we expect? Remember, you are looking at phosphorus NMR. Phosphorus can couple to this proton. What will happen? It will become a doublet. And then it is also coupled to 3 equivalent fluorine atoms. Then what will happen? Each line of this doublet will become quartets. You can see that there are 2 quartets here. One quartet is this, this, this and this. Other is this, this, this and this. There are 2 quartets. And this separation, one large separation correspond to the HP coupling. Other separation of the quartet gives rise to PF coupling. So this is the case where in the heteronuclei, phosphorus has coupling with 2 other heteronuclei. As a consequence, what you are going to see is 2 doublet of 2 quartets here you are going to see. This is 1 quartet, this is another quartet. See, very easily you can see the 2 quartets which I will show you here. See what I have marked here. See, this is one quartet which are marked in red arrows, other is another quartet which are marked in blue arrows. So very easily you can analyze this carbon phosphorus spectrum. Okay. We look at the boron NMR, something interesting. Boron has 2 isotopes, boron 10 and boron 11. Boron 10 is spin 3, natural abundance is 20%. Now I am looking for the boron NMR with coupling with proton of this molecule BH4. You should know that by now there are 4 chemically equivalent protons present. What is the splitting pattern you expect for boron? Boron 10 is spin 3, 2Na plus 1, you adapt this one. See, we are now have 4 protons coupled, 2 into 4, proton spin is half plus 1, you will get 5 peaks. Exactly we see 5 peaks. This is because of proton coupling. This is the boron proton coupling we get by measuring this adjacent peak separation. Why not we do boron 11 NMR? This is possible. Same molecule you do boron 11 NMR. Again it is coupled to 4 equivalent proton, identical 5 line pattern you get. Only thing is the coupling is different now. Because boron 11 proton coupling is 65 Hertz. In the previous example it is about 27 Hertz. Pattern is the same. It is 5 line pattern. So intensity pattern again goes by the Pascal triangle, you can see that. Now what happens in a molecule like this? If I take proton NMR, I am not looking at boron NMR, proton NMR of this molecule, you can see very interesting things do happen. Boron 10 has spin 3, abundance 20%. Boron 11 has spin 3 by 2, abundance is 80%. Now how many peaks you expect? For boron 10, put the 2Na plus 1 formula, very simple. Okay. In the case of boron, spin is 3, 2 into 3 into spin is, boron spin is 3 and there is only 1 boron is there, plus 1, 7 peaks you get. In the case of boron 11, 2 into 1 into spin is 3 by 2 plus 1. So how many peaks you get? You get 4 peaks. So boron 11 gives you 4 peaks, boron 10 gives you 7 peaks because of different spins. Boron 10 has 3 spin is 3, you get 7 peaks. You will see 1, 2, 3, 4, 5, 6, 7. 7 peaks you see. Easily you can say they are from boron 10 because of the multiplicity. At the same time natural abundance is 20%. See, their intensity is 20% less than this. This is 80%. If you take this as 100, this is 20% of that. Okay, that is intensity ratio 1:4. This is intensity 1, this should be 4. Intensity ratio is 1:4 here. So very easily you can say these 4 peaks coming is because of boron 11 and these 7 peaks are because of boron 10. So now I will take the example of mercury NMR. Mercury has two NMR active nuclei, mercury 119 and mercury 201. 119 is low sensitivity spin-off nuclei and gives sharp peaks. Let us take mercury NMR of this molecule, methyl mercury, dimethyl mercury. When you take the mercury NMR, you get a very single peak, that's all, sharp peaks, nothing else. But there are chota peaks here. What are these peaks? They are the satellites. They are the peaks which are coupled to carbon or proton. We will see which is which later. See, now if you see this gives peaks also coupled to either carbon, either carbon of this or proton group, either of them. We can see now, you can measure the separation from the other spectrum and understand. Now if you take the proton NMR of this methyl mercury, dimethyl mercury, and you can see mercury couplings appear as satellites here. This is what I said. We are going to see mercury satellite. Measure this separation, 100 hertz. Go back here, measure this separation, you will find out what are they. So this is the mercury coupling, 2 bond coupling of mercury with proton. Okay. So in the proton spectrum, mercury appears as satellites. Of course, you can also see proton coupled. Proton coupled, how many you expect? We saw that mercury very easily we can work it out. There are 2 methyl groups are present. What are the 2 methyl groups present? When 2 methyl groups are present, we worked out the pattern. See, when mercury will split into quartet because of one methyl, and each then is a quartet become another quartet because of another methyl. So what are the pattern you are going to get? A septet. We observed that, we worked out in the proton spectrum the multiplicity pattern. That's why explicitly we took example to see if one spin is coupled to 2 methyl groups of equal coupling, this is the pattern you are going to get. This is a proton coupled spectrum. Okay. The same thing you can see mercury NMR, but proton decoupled. Break the coupling with proton. Then you are going to get 2 peaks here. What are these 2 peaks? You are breaking coupling of mercury with proton, but not mercury with carbon. So these are the carbon mercury couplings which, because carbon is 1% abundant, which come as a satellite here. This is the mercury carbon couplings. So this is how you can understand the mercury spectrum. But you can ask me, why not we see carbon 13 NMR? Because this methyl mercury, we have mercury, we have carbon, we also proton. These are different nuclei. You can study this proton nuclei with carbon coupling, and you can see HD mercury satellites. You can see carbon by coupling with proton or decoupling with proton to see this one. You can see mercury resonance and then decouple with proton. Varieties of possible experiments you can do. So now if you see the carbon 13 NMR of dimethyl mercury, and you are seeing the mercury 119 coupling, you see here these 2 are the peaks. And the intensity pattern tells you the percentage of abundance of this mercury. Okay. If it was to be carbon 13, it is 1%, and 1% split into 2, it is 0.5%. But here you see, this is much better. This intensity is much better. The abundance of this mercury is much better than that of carbon. So from carbon 13 NMR, you see mercury satellites, and from this you get mercury carbon coupling. Sometimes huge coupling. Remember, J coupling of nearly 700 hertz you see between mercury and carbon. Okay. So like this, what I wanted to say is, n number of exotic nuclei you can consider. We can take lot more nuclei. I can give you an example without even showing the spectrum. Common we see tetramethylsilane. Go to silicon NMR. The proton NMR we saw carbon single peak in proton, use as a reference. In carbon 13 NMR, you got a single peak because we did broadband decoupling, used as a reference. Now go to silicon NMR. Again do broadband decoupling. Carbon is 1% abundance, naturally you don't see satellite, let us say, you get single peak. Now I will do one thing, I will bring in the coupling of carbon proton to silicon. How many patterns you expect? Very interesting, you understand. For example, tetramethylsilane, CA3, CA3, CA3 and CA3 are there. So now there are 12 protons, equivalent protons. If it is coupled to silicon, how many peaks we expect? Remember 2Ni plus 1. N is 12 here. 2 into 12 plus into half plus 1. So it is 13 peaks you expect. Go back and see, record the silicon NMR of tetramethylserine with proton coupling. You will see 13 peaks. So that's how, looking at the multiplicity pattern, using the simple formula I gave you, when you have equivalent spins, when they are non-equivalent spins, using the familiarity approach, and depending upon the coupling strength, chemical shift information, and depending upon their abundance and everything, you can give for a given molecule, you can do n varieties of NMR spectra you can obtain, and correspondingly you can analyze all of them to get the information. In a molecule like this, you can do carbon 13 NMR, proton NMR, silicon NMR. In silicon NMR, you can do proton coupling. In carbon 13 NMR, proton decoupling you can do, or proton coupling you can do. So all these varieties of experiment you do depending upon the information you want to derive. So this is a basically broad view I wanted to give you about the analysis of the spectrum of molecule, different type of molecule, different molecules and different heteronuclei. I hope you got the idea of how we can go ahead and analyze different spectra. But remember, all these things I explained in detail with number of examples in the previous course. This is only to make you, take you along with me. I explained this. Those who want to get more information, please go back to the previous course. So I will stop here now, but remember today what we discussed. In this class we analyze varieties of spectra, proton spectra, carbon spectra, nitrogen spectra, and then we understood how we get the pattern. Boron spectra, for example, if you take BH4, look at the boron NMR coupled to proton, you will get for boron 10 isotope, boron 11 isotope couplings will be there. One gives you 7 line pattern of 20% intensity, other gives you 4 lines of 80% intensity. So depending upon the isotopes, depending upon the abundance, you can see how many peaks you are going to get. Each of them can be interpreted with the knowledge of the coupling, with the knowledge of the chemical shift, knowledge of the abundance, knowledge of the sensitivity, everything. If you use any spectra which is given, can easily be analyzed for any molecule of any nuclei. So I hope with this gist you can go and practice with more spectra from more number of books available. You will be able to get lot of information and you will become a master. So I will stop here at this stage today, and next class we will go for a different topic. Thank you.